Okay, so today we will discuss about differentiation. So, essentially, if we are studying a motion and if the particle is moving on a straight line, then everything is very nice. But in reality, that is what it's not going to happen all the time. So, when Newton first time started to study the motion and gravitation, then found that this is not a very uniform motion, then how to study them mathematically. So, now in loose sense what he proposed that linear means what? I mean it is almost kind of a straight line. Now, he proposed instead of looking at the function which are linear, let us look at the function which are locally linear. So, in a loose sense what is a locally linear function? This is a linear. Now, suppose if I look at this function, something like this, the motion is going. Now, if I look from here to here, then obviously I can find the curve. Now, if I look here to here, still there is a bending. Now, you come very close. So, basically if you look at on a very narrow window, the small window, the function will look like a linear function. That is what intuitively is locally linear, whereas instead of, suppose I have a function like this. Now, at this point, I mean whatever the small window you make, but still the function is not going to look like a straight line. That is what Newton wanted to, he had proposed that let us instead of looking at the linear function, we can think of looking at the functions which are locally linear. Well, what is a linear function, or a function we say that which is an affine function if f of x equal to m x plus c. So, as we know this function is, we are familiar with this. So, this is m x plus c. Now, if c is equal to 0, then we say that the function is linear. That means, this is a line which passes through the origin. So, in that case, in this linearity, what happens? If I take x plus y, f of x plus y is equal to m times x plus y, which is equal to m x plus m y, which is equal to f of x plus f of y, and also f of alpha x is equal to alpha times x. Alpha x is a real number, and so this is alpha times f of x. Now, suppose f is an affine function. This is what it is going to look like. Suppose this point is x 1 and this is x 2. So, now when I am, this is x 2. Now, when I am going from x 1 to x 2, the function is increasing from f of x 1, this is f of x 1 to f of x 2. So, the increment is going to be f of x 2 minus f of x 1, that means which is equal to. So, this is f of x 2 minus f of x 1, and this is nothing but x 2 minus of x 1. So, then f is, we have taken this is equal to m x plus c. Therefore, f of x 2 minus f of x 1, this is going to be m of x 2 minus x 1. Thus, what in case of an affine function, suppose if I take my x 1 and x 2 here, then this is f of x 2 minus x 1. So, now as you can see that the ratio of this divided by this is going to be equal to m. Now, this m is going to, does not matter where your x 1 and x 2 are. The ratio f of x 2 minus f of x 1 divided by x 2 minus x 1 this is going to be constant, and this essentially, as you can see, that this is the slope of this line. So, that slope is going to be constant, I mean wherever you are going to take. This fine function, what we get is that f of x 2 minus f of x 1 divided by x 2 minus x 1, this ratio is constant always. That means, it is the ratio is same independent of the position x 1 or x 2, wherever you take, this is going to remain the constant. So, now this suggests that now let us try to define what Newton meant by locally linear. Now, let us consider the function f, which Newtonian quotient is, this is f of x Newtonian quotient, I will say that f of x 2 minus f of x 1 divided by x 2 minus x 1. In case of affine, this is constant. Now, let us take which is nearly constant. So, what is nearly constant? Nearly constant means this is equal to, this ratio is equal to m plus some function of x 1 and x 2. Okay. Now, this function delta of x 1 and x 2, if I come close to x 2, x 2 come close to x 1 and x 2 are difference is very small. So, this should go to 0. So, therefore, in that case what do we get is that the for close by points, if limit in the limit sense x 2 minus limit of x 2 converges going to x 1, f of x 2 minus f x 1 divided by x 2 minus x 1 is equal to m. So, this is now suggest us to define what the function is going to be differentiable. So, we will let's take I be an interval which is not a singleton, which can be closed, open, infinite interval, half closed, half open, anything, but not a singleton. Now, if let us take a point x in I, and we say that a function f is differentiable at x if there exists a mx which depends on this x, such that limit h goes to 0, f of x plus h minus f of x divided by h. Look at this, suppose if you have a function something like this, now you have a x here which is defined in this interval, you have a x here, then limit means this is x plus h, x minus of h, this is what the interval. So, now suppose this is x plus h, h is if you take to be positive. Now, f of x plus h minus of f of x by h, this is nothing but Newtonian quotient. Now, if h goes to 0, that means x 2 here is x plus h, x 1 is x. So, x 2 minus x 1 is h. Now, x 2 goes to x 1 means h goes to 0. So, if this limit exists, that is what we say that which is locally linear, right. So, now this is what we will now say that if limit h goes to 0, if this Newtonian quotient is limit exists, and that is equal to some number which is dependent on the point what you are choosing. If this limit exists, then we say that f is differentiable at the point x. Now, as you can see that here we are talking about the limit, that means our f need to be, our f need to be defined on such a point. Suppose if you are taking a b interval, then any point inside the open interval a b, I can define x minus of h, x plus h, because I am only interested in small h. So, I can accommodate x minus of h, x plus h for small h inside this a b. But if I am taking my x to be at a, then x for any positive h, x minus h, a minus h does not belongs to closed interval a b. That means, I do not have any information about the function on this side. So, at the end points, similarly at b, I do not have the information on this b to b plus h. So, I cannot talk of the derivative at the end point. So, now whatever interval we am taking, so except the end points, we are talking about the derivative of the function if it is a finite interval. So, now this another way of writing is that now I take a function c, I take a point c on the interval I say that f is differentiable at c if f of x minus f of c by x minus of c, that is the Newtonian quotient, limit x goes to c, this exists. If this exists, then I call that real number which is dependent on c to be f prime of c. Okay. Now, let us do some example which you have done it in your class 12. So, let us just take this f of x equal to x to the power n, where n is a natural number. Then of course, f prime of x is limit h goes to 0, f x plus h to the power n minus of x to the power n divided by h. Now, by binomial theorem, you expand x plus h to the power n. Now, x to the power n, x to the power n, which means k equal to 0 term will get cancelled. So, whatever the term remains, they will have a factor of h. Now, the first term for k equal to 1, we are going to get a factor of h, and in the rest of the thing k greater or equal to 2, that will be h square h cube. Now, if you divide it by h, then only the first term will become independent of h, and rest of the terms in this numerator is going to contain h. Now, when limit h will go to 0, all these terms will go to 0. So, only that first term k equal to 1 term is going to survive, and that is nothing but n, k equal to 1 is n, x to the power n minus of 1. So, derivative of f of x equal to x to the power n, this exists for all x real number x if n is a natural number, and its derivative is going to be n times x to the power n minus 1. Now, let us define f of x equal to square root of x. So, obviously, this function can only be defined if x is greater or equal to 0. Now, if we are here, we had been taken that f is from closed interval 0 to 1. So, this function is pretty much well defined. Now, in order to talk about the derivative of this function, obviously, we do not know what happens. This function is not defined for negative numbers. Also, no information is given to us when x is bigger than 1, because we do not know after. So, this can go like something like x 0 to 1, and rest it can go like this, it can go like this, it can because we do not have any information. So, only we have information on 0 1. Now, let us so we can only talk of the derivative of x when they lie between open interval 0 1. So, in that case we know that what we need to show is that the limit f of x plus h minus f x divided by h should exist. Now, this is square root of x plus h minus square root of x divided by h. So, this is a usual technique, I mean which we are quite familiar with. So, let us to get rid of this problematic thing square root of x plus h, if I multiply and divide by square root of x plus h plus square root of x, then this is going to be a minus b into a plus b. So, this is this square minus this square, which means x plus h minus of x divided by h times this. Now, you can see that this h and h, this goes away, this h and h gets cancelled. So, 1 by square root of x plus h plus square root of h. Now, if limit h goes to 0, then this guy goes to square root of x, this goes, this is square, there is no h here. So, this is square root of h. Therefore, this becomes 1 by 2 square root of x. So, derivative of x, if x is greater than 0, this is of f of x equal to square root of x, this is going to be 1 by 2 times square root of x. There is nothing holy about this, we can always define this function as f from 0 infinity to r. We can change our domain. So, if the domain is given to be closed 0 open infinity, then you can say that f is the differentiable function in the open interval 0 infinity. Now, let us look trigonometric function. So, most familiar is sin x. Now, f prime of x, now the sin x, the domain is on the entire real line R. So, now one would like to check that for every x whether this function is differentiable or not. So, in order to see that, we need to find that whether this limit exists. If this limit exists, then that is going to be f prime of x. So, this is h goes to 0 sin x plus h minus sin x divided by h, that is the Newtonian quotient. Now, we know we have the formula of sin a plus b. If I apply that, then this is going to be sin x into cos h, this is plus sin h into cos x minus of sin h. So, this is going to be, if I take the sin x common here. So, this is sin x into cos h minus of 1 divided by h and plus sin h by h cos h. Okay. So, as we know that this we have calculated that the sin h by h limit h goes to 0 is going to be 1. Now, what we need to calculate is this object. Now, this we know that this is minus 2 sin square h by 2. Now, this 2 sin square h by 2, what we know sin h by 2 divided by h by 2, h goes to 0, the limit is going to be 1. Now, for the sin square h by 2 divided by h we have. So, this is, I can say that this I will get sin square h by 2 divided by h square by 4. Then I need to multiply this h by 4, then this is nothing but this is equal to this. So, this is nothing but sin of h by 2 divided by h by 2 whole square into h by 4. So, now as h goes to 0, this one goes to 1, because sin h by h goes to 0 means h by 2 goes to 0. So, sin h by 2 divided by h by 2, that will go to 0, that will go to 1. Now, here you have h by 4, as h goes to 0, h by 4 will go to 0. So, the first term will go to sin x into 0 plus cos x into 1, which is going to be cos x. So, then what we say that now here is a function sin x, what we are saying that the domain is R and it is differentiable at each and every point of R. So, now similarly, wherever f is defined, suppose f is defined on an interval I, we say that f is differentiable on I, on the entire interval I, if for each x f prime of x exists. That means, f is differentiable at each x belongs to I. So, obviously, if you have an open interval, then you can say that f is differentiable on I. If you have a closed interval, then at the end point we have a problem. And here in this language, we can say that the function f of x equal to sin x is differentiable on R. R is an interval, open interval minus infinity to infinity. So, f is differentiable on R. Okay. Now, let us try to see that we have read continuity. Now, if f is, when f is not differentiable, that is that we must try to address. So, first thing we are going to notice is that obviously, intuitively when we are saying f is differentiable, that means here in a sense that we are saying, okay, so here is an interesting phenomenon. This Leibniz saw this derivative in terms of the slope tangent to a curve at the point, because you can see this. Suppose if I have this curve, now I want to find the tangent at this point. Unless and until I know the slope, I cannot find the tangent this. So, now how to find what is this equation of this? So, for this at least I will need 2 points, but we do not know, we have only 1 point given to us. So, what we do is that we join this point, then we take a smaller point. So, now this is nothing but going to, this quotient is going to be f of x 2 minus f of x 1 divided by x 2 minus x 1, and that is the Newtonian quotient. So, essentially if I have a curve f of x, y equal to f of x is given to be a curve, then this Newtonian limit of the Newtonian quotient, the derivative is nothing but going to be the tangent of that curve at that point. So, it is expected that it is going to be continuous at that point, that is what we are saying. If f is defined on an open interval I, if f is differentiable at a point C, then f is continuous at C. So, the necessary condition for f to be differentiable is that f has to be continuous at that point C, but it may not be the sufficient condition. But first let us try to prove that it is a necessary condition. So, now what we need to show is that in order to show that f is continuous at a point C, so we must show that limit x goes to C, f of x is equal to f of C. So, now we want to look at f of x minus f of C. So, let us take the point x which are close to C, but not equal to C. So, therefore, x minus of C, it is not equal to 0, because x is not equal to C. So, I can divide by x minus of C. So, this is, I will divide and multiply. Now, if I take the limit, what I know that limit of f of x into g of x, x goes to a, is equal to limit f of x into limit g of x, provided both the limit exists. Now, in this case, the first one, this limit must exist, and this limit, as we know that it is going to be 0, because if x goes to c, this is 0. Now, if this limit exists, then we can split. So, what we are going to get, that is going to be equal to 0. Now, this is exists because f is differentiable at a point c. Therefore, this goes to f prime of c. So, this goes to f prime of c into 0, which is equal to 0, this as x goes to c. However, the converse may not be true. Now, let us take, as we can see that intuitively also we have seen that when we are talking about Newton's loose sense of locally linear, we saw that this sort of, if our function is this, then suddenly it is changing the direction, then however small neighborhood we take, we are going to find that direction. So, this is not going to be a straight line. What Newton suggested is to look at in a small window, if I look at, then they may look like a straight line. So, this sort of thing, whenever it is there, then this is not going to be, they are not locally linear. So, for example, let us look at this mod x. Now, mod x, if you draw the graph, then on the positive side it is x, and on the negative side it is minus of x, which means positive. So, here you know that there is a change of direction, drastic change of direction at the origin. So, now if I want to look at the derivative of this, that means we would like to look at f of 0 plus h minus of f of 0 divided by h. So, f of 0 plus h is equal to mod h, this is equal to mod h minus of 0, f of 0 mod 0 is 0 divided by h. Now, as limit h goes to 0 plus, then mod h is going to be h. Therefore, this is h by h, which is equal to 1. So, limit h goes to 0 plus, the right hand limit is 1, and the left hand limit is a mod h when h is less than 0, then mod h is going to be minus of h. So, this is equal to minus of h divided by h, which will be equal to minus of 1. Therefore, the left hand limit is not equal to the right hand limit. Therefore, the limit does not exist. Hence, f of x equal to mod x is not differentiable. Okay. So, now what you can see the algebra of the differentiation, if you have a function, two functions f and g, which are defined on an interval I, and both f and g are differentiable at some point x belongs to I. Then what we can say is that f plus g, you see this is also a function f plus g of x, we have talked this many times, f of x plus g of x. So, f plus g is also going to be differentiable at that point, and its derivative is going to be the sum of the derivative, f prime of x plus g prime of x. Similarly, if we take a scalar alpha, hit that with f, that is alpha f is another function. So, if f is differentiable, then alpha f is also going to be differentiable for any alpha belongs to R, and that is going to be alpha times f prime of x. And if both f and g both are differentiable, and then multiplication function f g, that is also going to be differentiable, and the derivative of that is equal to f prime of x g x plus f of x into g prime of x. First derivative into second plus second into the first function into the derivative of the second function. Interestingly also, if g of x is not equal to 0, then I can define f of x by g of x at that particular x. Now, look at that g is a continuous function. If g of x is not equal to 0, either it is going to be a positive or negative value, then there will be a neighborhood what we have seen around x in which g of x will be positive. So, if g of x is a continuous function not equal to 0, I can find some delta such that in x minus of delta to x plus delta, this is on this function g of y is not equal to 0. Now, in this neighborhood I can define f by g. So, I do not have any problem of taking the limit as h goes to 0 x plus h, because this g of x plus h is very much defined for small h. Therefore, and the derivative of that is nothing but g f prime of x g of x minus f of x g prime of x divided by g square x. This you can prove it just by the way we have proved all this thing in the limiting case and as well as in the for the continuity. Okay, thank you. We will continue with this.